I've finished up section 2.5. Start the discussion of proofs. A proof is a convincing argument that uses deductive reasoning. Deductive reasoning being the structure that states a truth based off previously known truths. The idea of a proof is to make a strong argument, and we want to make sure that we don't have any gaps in our proof. Okay, so we want to essentially answer the question why something is the way it is, and then our answer to that be indisputable. Okay, it cannot be torn apart and shown to potentially be an incorrect argument. So the proof logically shows why conjecture is true. Some things that we're going to do, and we've talked about this with the law of syllogism already. Statement D is going to be true because statements A, B, and C all followed a logical pattern that were true. That then allows D to be true and be indisputable. Okay. So what we'll do, we've got a mechanism that we go through in geometry called a two-column proof, and it's really more of a kind of a rough draft. If you're writing a paper in English class, you're going to do an outline. You're going to do a rough draft. You might do another rough draft, and then you'll put that together in your final piece. And then you would present that final piece, or you'll turn that final piece in, or if you're an author, you would publish it. Okay, so that's kind of what we're doing here. A two-column proof is kind of the outline / rough draft of an actual proof. Okay, a lot of times what we would do, and we'll do a couple of these throughout the year, is that we'll do a two-column proof. It'll organize our ideas, much like an outline does or a rough draft does, and then we'll finalize that in paragraph form. What's going to happen in a two-column proof is that they're going to give you, you're going to prove essentially what we call a theorem. So it's going to say some if statement, and then it'll be then some then statement. So the if part is if we're going to prove this statement, okay, we're usually proving, usually always proving the conclusion. We're going to make an assumption that this is true. This if part is what we have in front of us. We call that given information. We know that to be true. Okay, that's happening in front of us. Can we prove the conclusion? Okay, so in an if-then statement, the hypothesis is going to be your given for a proof, and the conclusion is going to be the actual prove statement that you're setting out to make an argument for. So really what we would have here would be the statement that they would have started us off with. It would have said if measure of angle 1 equals measure of angle 3, then measure of angle AEC is equal to the measure of angle DEB. That's how it would be presented to us, and they would say at the beginning of the question, they would say prove, and they'd put like a colon or whatever, and say prove that if measure of angle 1 equals measure of angle 3. So you know that this is happening in front of you. That's truth that you know. Based off of that truth, can you deduce that this is true? Can you come up with a logical argument of why, if you know this is a true statement, why that would be true? So what we do is we create a two-column proof. Left-hand column is going to be what we call our statements. Okay, those are going to be the arguments that we kind of piece together using the law of syllogism, law of detachment, those sort of things. And over here will be your reasons of why that would be true. Okay, so statement 1 is made. It's always going to be given. Statement 2, we have to develop, and we'll talk about how we develop that. But then this would be the reason why this was able to be said. So the first statement is usually the given statement. Each statement should be followed logically from previous statements. And the last statement is always going to be what you want to prove. Okay, so it kind of tells you once you have this matching to that, you're done. Some proofs will be 5 steps long, some will be 3, some will be 13. It just depends on what you're proving and what information you have at your disposal when you start that proof. I strongly suggest that you guys kind of print this off and make this a piece of paper that you can go to on a regular basis. You're going to struggle sometimes with proofs. Some people get the hang of them right away. Some people struggle and struggle and struggle. But if you are a person that struggles, this is a great tool to help you. Okay, you're not going to find this in any textbook. This is my kind of convention on how you can get yourself through a proof. First thing you're going to do is write down the given statement and reason in number 1. Okay, or line 1. Second thing you're going to do, you're going to look through the information regarding equal or congruency signs that was provided in the given, and you're going to put that in your picture. You're always going to have a picture. Okay, it's very hard to do these proofs without labeling and filling in a picture, and you'll experience that later on. You don't see it too much today, but when we get into the next chapter, especially if we don't label things, we don't fill in congruencies, inequality in our pictures, the proofs become almost impossible to complete. Step 3 says look at your given information, and you're going to look for vocabulary words. Okay, if you see a vocabulary word, we're going to write down what that vocabulary word provides us in the next statement. Okay, so let's say that I have the word midpoint in the given. I'm going to go down in my next step and I'm going to say, okay, I have the word midpoint. What does that tell me about my specific problem? What 2 segments would be congruent because I know I have a midpoint? I would write those 2 segments down, and then my reason on the right-hand side in that next step would be definition of midpoint. Okay, so that's what statement 3 here, or step 3 is talking about. And you'll do that for however many vocabulary words that you have in the given. And if you generate a vocabulary word in your statements on the left-hand side, you will do the same thing. Okay. Step 4 says, from what you learned using your vocabulary, indicate any equality or congruency statements that within your picture. So that's repeating step 2 essentially with the vocabulary that we just came up with. So if I show that 2 segments were congruent or 2 angles were congruent based off of definition, I'm going to go to my picture and draw that in. Step 5 says look at your picture, and this is going to be early on. The further we get into the text, the more things we can add to this. But it says look at the shapes that you're dealing with. If it's angles, then you instantly want to start thinking about angle addition. If they're segments, you want to think about segment addition. Eventually, if they're triangles, we're going to try to prove triangles congruent. So, that'll be chapter 4, and I'll open your eyes to that when we get there. But right now, the main 2 tasks that we will be working with is angle addition and segment addition. Step 6 says now you want to look at several statements that you have made, and from the above steps, and see if you can combine them to make a new statement. So this step 6 is essentially the law of syllogism, and this is the hardest step throughout here. If you can get to step 5, then chances are you've probably got 80% of the proof done, and that's just by looking at vocabulary and listing things in our pictures. Step 6 is then combining those statements that we've already made. If I have statement A is true because, so say we've got statement B is true because A was true. Can I stitch those together to get statement C to be true? That would be a completely new statement for the problem. And that's what statement 6 is talking about here, step 6 is talking about. And that can be a difficult task, okay? And you're going to get better at those through practice. Step 7 says that new statement may lead to what you want to prove. Okay, it might end up giving you your proof statement, and then you'll be done. It might lead to a new statement that is not your proof, but you could take that new statement and stitch it together with previous statements to create something new again. Okay, and we keep playing that game until we've stitched things together enough to make our our prove statement, or the thing that we're set out to prove, um, show up in our statements. As we do an example, we'll come back to this and we'll talk about this process. Pretty much every single proof that we do throughout the year, you'll hear me talk about this set of 7 steps. So this is the idea behind step 5 on the previous step. So step 5 said look at your picture, deal with angles or segments. You probably want to use angle addition, that kind of stuff. Here, so a very important part in writing proofs is analyzing the diagram for key information. This is what true statements can you make based on your diagram. That's right. So there's going to be usually, these statements that we come up with, but then there's going to be one missing piece that we can't figure out, and we're going to look at our picture and see if we can figure it out. And from the picture right now, we should be able to identify a couple things. We should be able to identify that segment DB is congruent to segment BE through the markings, okay? But we can also say that angle 1 and angle 2 are a linear pair just by looking at the picture. And if they're a linear pair, we know they add to 180 because we have a postulate that says linear pairs are supplementary. So there's a lot of stuff that we can look at our diagram from, and without being told explicitly in previous steps, we can come up with new information just from the picture. So that's kind of that's one of the harder parts of proofs as well. All right, so we're going to do a 2-column proof here. Now, early on, you're going to see a lot of your 2-column proofs. These statements are going to be filled in for you, and we just have to come up with the reasons. Or they'll have like 3 statements and then a blank one, and they'll have like 3 blanks over here. So like these 3 statements will be written, and then these will be blank. This here will be blank, and this one will be filled out. Okay, so it'll be kind of a hit and miss hodgepodge of filling in statements and reasons. Eventually, the task will be we have a completely blank proof. We're given these 2 things, we're given a picture, and we come up with all the statements and all the reasons. All right. So, number one thing we're going to do, we're going to look at this, and this is exactly what I said earlier. Basically, what would be being asked in this problem would be prove that if the measure of angle 1 equals the measure of angle 3, then measure of angle AEC equals the measure of angle DEB. So our given is the hypothesis of some if statement, okay, or some conditional. So that's what we're given, and we want to prove then the conclusion. So the argument is, if you know this picture and you're given in front of you that angle 1 and angle 3 are the same, can you come up with the argument that AEC, that angle there, plus, or not plus, angle AEC is the same as this yellow angle DEB? And now here's my question. We're gonna do this real quick with just some numerical values. If I said angle 3 was 35 degrees, the given says that angle 1 must be the same thing. Angle 1 is 35 degrees. Okay. Now AEC is that angle there. So angle addition says AEC is this 35 degrees plus angle 2. Let's say angle 2 is 10 degrees. So this yellow angle would be 45 degrees. Well, if I look at, I said yellow, the green angle would be 45 degrees. This yellow angle, which is DEB, which is that one there, AEC was the green one. The yellow one's also 45 degrees. Well, that makes sense then. If I take 1 equals 3, start off with that thing being true, then this has to be true because all I'm doing is to get AEC, all I'm doing is adding angle 2 to angle 1. And to get DEB, all I'm doing is adding angle 2 to 3. So I'm starting off with two things that are equal. I'm adding the same thing to both sides, so they must be equal. And what I've shown here is what we call a specific case, because it works with 35 and 10, but what we would have to actually do is show that it works with 36 and 10, and then 37 and 10. And then we'd have to go to pretty much any value you ever think of. We have to show all possible situations. So what we do, instead of showing all possible situations numerically, we use these symbols to say measure of angle 1 equals measure of angle 3. I don't know what they are, but they're standing in essentially for all those values that angle 1 could be, all the 35s and 36s and 37s and 35.2s and the 12.45s that angle 1 could take on. And that will prove then that no matter what I start with, 1 being equal to 3, no matter how big those angle measurements are, I should be able to get to this conclusion here. So first thing we're going to do is we're going to look at measure angle 1 equals measure angle 3. That's given. Okay. The next thing we do is say, okay, well, they say measure of angle 2 equals measure of angle 2. That angle right there is equal to itself. If you remember from what we talked about yesterday, when something is equal to itself, that's the reflexive property. So that's the benefit of learning some of those properties that we talked about yesterday. Why are they going to do that? Well, let's look at this statement here. How do we go from that statement to this statement? Okay, well, if you think about it, statement number 1 and statement number 3, I'll highlight the things that are the same in them. Okay, both of them have angle 1 on the left and both of them have angle 3 on the right. What am I doing? I'm adding that to the left, I'm adding that to the left. Now, I don't know what measure of angle 2 is. Whatever that quantity is behind the scenes here, that symbol is standing in for. Maybe it was that 10 degrees, but I'm adding that to both sides. When you start off with something, a statement with two things are equal, and then you add the same thing to both sides, that's called the addition property of equality. That's exactly what you've done in situations like this. If I want to solve for 2x, I add 3 here, and I add 3 there. That's all they're doing. Now, we usually write it this way, but there's nothing wrong with doing it this way. Put them in line like that, and that's what's going on here. They're adding 2, and they're adding 2. Okay? Now, this step here is step 5 up in that set of steps I gave you here, because now what we have to do is we have to look at our picture. And we have to think about what does our picture lead for us that we don't get from the given or we don't get from anything else that's up here. And what this picture is telling us is that if I take that angle right there, which is angle 1, and add to it angle 2, doesn't it give you that angle right there? If you remember back to the first chapter, when I take two smaller adjacent angles, add them together, and I get the larger, bigger angle, that's called the angle addition property. Postulate, sorry. I'm not really keen on you guys remembering whether it's a postulate, it's a property, it's a theorem. I want you to know what the statement is, that it exists. Put that tag on the end, whether it's a postulate, theorem. I'm not a big stickler on that. Obviously, if you can learn those, it's better, but you won't lose points for that kind of stuff. The next one says, let's take angle 2 and angle 3. Angle 2 and angle 3, and add them together. Do I get DEB? Do I get that angle there? And again, it's angle addition postulate. That's why they're both under statement number 4. Okay. So now, the hard part is these things are now all true. We've shown why they're true. Okay. Can we stitch some of these things together to come up with a new statement? That is also true because these were true. And here's how this is going to work. If you look at statement 3 and statement 5, they are identical. Now, they look different, but they are identical. Because if I look here at 1 plus 2, look at statement number 4. Don't we say that 1 plus 2 is AEC? So what they're going to do from statement 3 to 5 is where in 3 where we say we saw 1 plus 2, we're going to replace it with this AEC. It's going to be right there. And then in statement 3, we see 3 plus 2 right here. Well, 3 plus 2, we said that that's the same thing as DEB. So down here, we get put in DEB. So statement 3 and statement 5 are the same, but in statement 3 where it said 1 plus 2, we're going to rewrite it as AEC, give it a different name. If I look at 1 plus 2, and 1 plus angle 2, that is AEC. Now, that task of taking this and replacing it with that, something that it's equal to, and taking this and replacing it with that, something that it is also equal to, replacing something with what it is equal to is called substitution. And because it's using equality, the substitution property equality. This is really the same type of proof, okay, and we'll do the whole thing here. But they're saying if, given this picture, if you know distance AC is the same thing as BD, can you prove that AB is equal to CD? So start with statements. We'll have reasons. This one's going to require us to do the whole thing. But think about this. AC, if that distance right there, let me highlight it, be easier. This blue distance is the same thing then as this green distance. That's what they're saying. Would you agree if those two things are the same? Let's say they're both 20 units. Do they both have BC as part of them? Let's say BC is 5 units. If I remove that 5 units from both 20s, you're going to get this distance right here to be 15, and you'll get that distance there to be 15. That's A, B, and CD. They'd both be 15. They'd be equal, like it's saying right there. So if you can grasp that idea, all we're going to do now is just be a little bit more vague with it. We're not going to give it specific values of 20 and 5, because that shows that it only works for 25, and we have to show it does it work for 20 and 6, does it work for 20 and 7, does it work for 21 and 5, does it work for 21 and 7, and so forth. So there's an infinite number of specific cases that we'd have to show, and we obviously can't do that, so we have to use these symbols. Okay, and these symbols then represent all possibilities, all values that those segments could take on the length of. So the first thing we're going to do is going to write step 1 that AB is equal to, AB is AC. AC is equal to BD, and that's given. Okay. The next thing, so going back up to those 7 steps I gave you, you want to look in your given and see if there's any vocabulary words. And what I mean by that is, are there any written vocabulary words? In this case, there's not, so we skip that step. Okay. I do think it's kind of hard to do, but it is. I like to use highlighters to remind myself that those two things right now in my picture, I've identified them as being the same length down here. Okay. When there's overlap here, it's hard to put tick marks in here. So put a tick here and a tick there. It's hard to tell what does that red tick refer to. Is it referring to AB and CD, or is it AC to BD? So that's what I like to do. I like to highlight them so I know that those two things are congruent. Next thing I'm going to do is, okay, well, I don't have any vocabulary, so let's look at our picture. Let's look at our picture and see if we can make an argument about the green segment. So look at that green segment. I think we can all say that AB plus BC is equal to AC. AB plus BC is equal to the entire distance AC. And we could probably do the same thing with BC, CD, and that will give me B to D. And because we're talking about segments and we're adding smaller segments together to get larger segments, this is the segment addition postulate. Okay, now I'm going to use these two things together. Right now, we see that we've got AC and BD right here. They've been renamed as these sums. So we have AC and BD right there. So step 1 and step 3 are actually going to be the same thing, but instead of writing AC on the left-hand side, I'm going to write that. I'm going to write AB plus BC. And instead of writing BD on the right-hand side, I'm going to write that. BC plus CD. And all I did there is, like I said, I took statement 1. On the left-hand side, I replaced it with something that it was equal to. On the right-hand side, I replaced it with something that it was equal to. So that's substitution. All right, so now the next thing is, look at that statement. You notice anything? You notice an amount right there and an amount right there. Now, I don't know what those numbers are that are being represented by that symbol BC, but I do know whatever it is on the left and it's on the right. I'm going to say that BC is equal to BC. Now, this is just a procedural thing that we usually do. Think about if you had like 2x plus 5 equals 10, you would put minus 5 here, minus 5 there. You tell everybody what you're about to subtract from both sides is the same. That's what I'm doing here. BC, the same thing as BC. It might be evident, pretty obvious, okay? Some authors leave 4 out. A lot of them put 4 in. I think the more that we add into our proofs, the more exposure we get to these ideas, but two, the less potential we provide an audience to kind of attack part of our proof. So now, if I think about this, so BC is on the same value on both sides, so they really cancel out, and what you're left with AB equal to CD. Is that what we were trying to prove? It's indeed what we're trying to prove. And if I wiped BC off of both sides because it was the same amount on both sides, that's the subtraction property of equality. You see a couple of these in your homework. Early on, especially, these are the types of questions that we see because we have most experience with this type of stuff. It's just a segment addition question. They're gonna give you C is the midpoint of segment AD. Okay, so C is the midpoint. They want you to show Y. They want you to demonstrate why X is equal to 6. Okay. So we know how to do this. We've been doing this for a lot of chapter 1, but now we're showing the why of that procedure, that process. So here it says C is the midpoint of AD. That was given. Okay, if we were thinking about the if-then statement that this would have came from, it would have said if C is the midpoint of AD, then X equals 6. So they would be asking us to prove that. So we got the given. So now here's where this is a vocabulary word. So always want to write our given and then look to see if there's vocabulary words in our given. So then we write down in statement 2, what does that vocabulary word give us for our particular situation? Well, since C is the midpoint of AD, it breaks this segment up into those two parts. And what do we know about those two parts? They have to be congruent. Why do we know they're congruent? Because we know what a midpoint does. We know what a midpoint is. And the way we know what a midpoint is that it's expressed in the definition of a midpoint. Okay? Now that when I provide a reason that says definition of midpoint, that's a shorthand way of saying that it is a point of a segment that divides a segment into two congruent segments. What is that? That's the actual definition. It's the phrase that I would look in the glossary of my textbook. If I looked up midpoint, it's going to be in bold, and then right underneath it is going to say this statement here. It's much easier just to say definition of midpoint, knowing that this is what that definition says. One thing that they like to do, because we're going to start doing some, because these are distances, when we do some substitution and subtraction and just doing algebra with segments and angles, we can't do algebra with actual shapes. We can only do algebra with numerical values. So right now these are shapes. We need to get and start talking about their distances or their lengths. So they go from AC, segment AC being congruent to segment CD. And then we say AC is equal to CD. This says congruent segments have equal length. You're going to see that that's a common phrase. You're going to see me write that as the definition of congruency. If you look up congruency in the back of the book, or you look up congruent segments, it's going to say congruent segments have equal length. Okay. So now these are distances. Well, look at AC. AC is represented as 4x. That's a distance. Now we can replace AC with 4x. We can replace 2x plus 12 into the spot of CD. So CD is on the right hand side here. Well, CD is the same thing as 2x plus 12. So that argument there is substitution. And it's of equality. So now they're telling you what you have to do. And then that next reason was subtraction. So if I'm looking at this, most people, I would argue, to be efficient, are going to rewrite the left hand side as 2x and the right hand side as 12. We subtracted 2x for both sides. I like to sometimes put, like, in parentheses after I do subtraction or addition, what did I add, what did I subtract from both sides? Now that we're here, how do I solve for x? We divide both sides by 2. So this reason here would be division property of equality. And again, maybe in parentheses I put that I divided by 2. I want to stop there. These are just some more of those individual phrases. Remember, so these are, do a couple. It says symmetric property of equality. If you know AB is equal to YU, the symmetric property just says we can flip that. So you can say YU is equal to AB. Reflexive property of congruence says something is congruent to itself. So PQR, POR, whatever that letter is, I think it's a Q. PQR is congruent to angle PQR. Here it says substitution property. It says if LM is equal to 7, and it says EF plus LM equals NP, then I can say EF plus 7 equals NP. They've told me what LM is. Anywhere I see LM, I can replace it now with 7. Symmetric property of congruence says if angle H is congruent to angle K. Symmetric property of congruence just means we flip. So then angle K is congruent to angle H. Distributive property would be 3x minus 3. Transitive property, remember, says this is why I like, or how I like to write the transitive property. It says so angle XYZ is congruent to angle AOB. That's the first phrase here. It says and angle AOB is congruent to angle WYT. I like to write it this way because I can visually then think about, well, let's put those on top of each other. You see the angle AOB is now that middleman, and then if I wipe it away, what am I left with? I'm with angle XYZ congruent to angle WYT, and that angle XYZ congruent to angle WYT, that is then the conclusion right there. That's just a brief 35-minute introduction to proofs. Okay, we will spend a lot of time in this course on proofs. They are structured arguments, indisputable arguments for why something is the way it is. And if we can get good at these in mathematics, then you can get pretty far in arguments about just regular everyday stuff. Okay, they're very this way of thinking is very, very useful if you can train yourself to think this way.